Let me extend a hearty welcome to Dr. Murthy, 1981 MSc Chemistry, if I'm correct, as Professor Swami said, is our esteemed alumnus. So on behalf of the SAIL and the university, we extend a hearty welcome to the esteemed alumnus, Dr. Murthy, and Professor Radhakrishnan, Professor Samar Das, my colleagues and students, and it's really nice to see the school children also here who are interested to listen to something about the comets. You would have seen the title. So I'll not take much time. Just like to mention that Alumni Cell is working for the last 2.5 or 3 years, primarily to engage with our alumni and strengthen our alumni connect. And last year we had a series of events organized by schools of physics, medical science, economics, management, humanities, and if I am casist, the part of School of Physics, and also Engineering, Science and Technology, which was generously supported by the IOE Directorate. And we had a series of distinguished lectures, and also we had alumni meets. And so that helped us, strengthening our connect. And we have been having, the connection before these lectures through a portal, which is very much there in the university website, the university's alumni portal. Every day we get our alumni registering the portal. So we have about 10,000 of our alumni who have registered on the portal and who get to know everything about the university every other day. Whatever happens in the university, be it lectures, workshops, conferences, and we also celebrate our alumni achievements. And it's really nice to see that we are able to connect now with our senior alumni. Thanks to Professor Swami that Dr. Murthy could make it to this distinguished lecture. And we will continue these activities throughout the year. And I request all my colleagues, all the heads and deans to support the cell in getting alumni contacts. And any event you want to organize with regard to alumni, we can always jointly organize so that we continue to strengthen our alumni connect. And they are our brand ambassadors and also, resource. So let me not take much of time. I think the children are interested to listen to Dr. Murthy. Thank you very much.
Good morning to all of you and welcome especially to the younger people in the audience. It's a great privilege to have Professor Murthy Gudipati, who is one of our distinguished alumni, to give a lecture here today. I think Murthy, Swami and Professor Kalidas Sen can vouch for his studies here several years back. And I think Swami will probably give a longer introduction. And I think some of his other classmates who are here. And Murthy did his MSc here and later on Ph.D. in Indian Institute of Science. And he moved quite a long distance, like comets do, from chemistry to astrophysics and cosmology and so on and so forth. So comets obviously are extremely interesting bodies. They are apparently very icy. None of us have been there, but this is what the scientists tell us. And he has been involved with this very famous mission called the Rosetta mission, which has the great distinction of having been the first orbiter to land its lander, Philae, is that the way you say it, on a comet, which has a very complicated name, but I believe it is called 67P according to Wikipedia, uncle. So this is a very amazing feat because it can circle the sun along with the comet and try to understand how many chemical processes happened in the universe, which of course have a great bearing on how origin of life happened on the earth, and in particular things like the origin of water, because these are icy celestial bodies. So they have water with various deuterium-hydrogen ratios, which become a good marker to try and analyze and understand from where the water on this earth came, because earth was obviously extremely hot in the beginning. So there was some point in time when water appeared on earth. And this is, I believe, one of the missions of this study. And I'm sure Dr. Murthy will tell a lot more about this. So I will leave the floor to him. And we are eagerly looking forward to his lecture. And great to have you here. Thank you.
It really gives me great pleasure to introduce Dr. Murthy Gudipati, who happens to be my classmate in MSc in this university during 1979 to 81. We forged a very strong friendship during that period, and subsequently we both moved to the Indian Institute of Science for doing Ph.D. He went to the Organic Chemistry Division, worked with Professor K. Venkatesan, and I joined the Molecular Biophysics unit, but we continued our friendship because we also stayed as roommates for a couple of years before we got our independent rooms in the hostels. Okay. I will not speak more about our friendship, which continued and continues. Okay. But let me say that he has done exceptionally well during his academic career. He did his bachelor's degree from the SRR and CBR College in Vijayawada, where he came college first. Gold medalist in the MSc in this university in 1981 batch. Best Thesis Award for PhD in 1987 from Indian Institute of Science. Subsequently, he went to do postdoctoral research at the University of Texas at Austin, worked with Professor Joseph Mitchell, and worked again exceptionally well with many publications, many in respected American JSES, which is an American Chemical Society flagship journal. Subsequently, he moved to Germany, and where he did another PhD or equivalent to PhD, which is called habilitation. And subsequently, he moved back to US and worked in a couple of places before moving to NASA Research Labs in Jet Propulsion Lab in Caltech, where he has been working in space missions, doing simulation experiments on related to the atmosphere that is present on planets. Because comparison of the two sets of data that is acquired from the simulation experiments and the acquired data collected from the space spectroscopy is what he does. And that is the one which he will probably speak about partly in today's lecture. He asked me specifically not to give a long introduction, so I don't want to speak more about him. Let him speak about what he does. Thank you.
It's very emotional and also privilege and honor to be here after 44 years. When I left this campus in 1981. I have been coming back, but probably not in an official form. I think it's connected now. Yeah. Can you see whether it is on? Look how. You don't need it. Yeah, look, I think I have water. You can take. I have water. Here's my face. Said all this. Okay. So just put up with me for a couple of minutes. Okay. Do we have connected? That's connected. Okay, good. Let's see. Yep. Fantastic. Yeah.
You're playlist.
Yeah.
Nice.
All of them off. Good. That's fantastic. And do you have a pointer? Pointer, Ella? Pointer. Okay. Good. Don't worry about it. Don't worry. Science can be done without show. Okay. So I'm really happy to be here, and especially to see the school students here. Thank you for being here. And you're the future. One thing I want to tell you is dream big work hard, don't give up, and don't compromise. Okay, that's very important. If you don't work hard, you cannot expect someone else to do the things for you. Okay? So if you don't dream big, you can never achieve anything bigger than what you are around. Okay. So that's what is important for you. Now, Central University of Hyderabad played a very key important role in my life. Like, Professor Swami said, and I'm really happy to see our teacher, Professor Kaldas, in here. And we just met with Professor Mehta, who was also our teacher. When we came here, we all came from small villages and towns. Hyderabad was the biggest town by then, our city. But Central University changed our lives in such a way that it gave us very strong foundations in whatever the field of studies we took. And in our case, it was chemistry. And that foundations actually led us to go even to the next places where we could flourish. And we could also take challenges on our way. We never were afraid of taking challenges. And the seeds of that thinking came for us from Central University of Hyderabad. Okay, I'm thankful for that. So today, I want to warn you, it will not be a small presentation. It will be a long one because I'm going to take you to the beginning of the universe until today. Okay? If anyone is tired, you can slowly, silently leave the auditorium. Unless the story is told in full, you don't appreciate what it is. Okay? And I'm going to tell you the story in full. So, every one of us, every human being, ever since we were able to think, have been asking this question. Okay? How, when, and why the universe came into existence. How life came into existence. I'm sure you would have asked this question in one or other form in one time or other in your life. Those who did not ask that question, please raise your hands. Okay, I see no hands raised. That means all of you have asked those questions. Okay, so important it is for us, for our existence, for our curiosity, and for our knowledge. And this is what we are going to go and take a deep look into. And also keep in mind that everything I say today is the frontier of research. That means nothing is set on stone. Nothing is set on stone. I repeat. Okay? There is nothing to believe in it. There is only one thing, that is to understand. Our state of understanding is what I'm telling you. And it could change as we progress our research, our understanding. Okay? Whatever I say here is work in progress, because this is something that we have been working on for generations, and it will go on for generations again. Okay. And I quoted this here not because of any other reason, but because even 5,000 years ago, let me see whether I can make it more. No, this one will not make it. Okay, that's fine. Even 5,000 years ago, people were asking the question. And they were puzzled and they were confused. And this statement here, a double negation, clearly shows that we thought we could not understand. Okay, that is the essence of this. Okay, don't take it. But so that means about the origin of life, about the origin of the universe, people have been thinking for at least 5,000 years or more. Okay, we are not the first one to think about. That's one thing that you want to keep in mind. By the way, all these slides I can give to Professor Swami as PDF later, and you can go through it. Some of these things I go really fast because there are 65 of them. Okay? So I want to constrain my field of discussion today, or presentation today. We want to understand how the conditions that are there, or that were there for life to start. Okay, these are all the conditions. These are the questions that we are also still continuing to ask and answer, but that will not be, covered in today's talk. Okay. So our story is today begins with: is there life on Earth? Can anyone tell me? Do we have life on Earth? How do you know that? We are there, right? Yes. So obvious. Okay? That is what we take it as granted, that life is there. We take granted that we have life here. But in order for the life to thrive, as we think our life and the biodome that we have, diversity, we need 4 minimum ingredients. I come to other conditions that are even more needed. But these 4 minimum ingredients are beautifully shown here in the half dome of Yosemite National Park, which I really like. Water is very important. Minerals are very important. Organics, that's we are all made of. And the blue skies are because of light, energy. So energy is important. Energy, water, organics, and minerals. These are the 4 important ingredients. And we want to see that there is so much of biodiversity. And especially in this campus, when we were there were only rocks and snakes. Now, 44 years later, this campus is so beautiful. Just go out and enjoy the biodiversity here. And these are the biodiversities that I see every day in my walk. And I make sure that I appreciate them, because as you come to the end of the lecture, you will understand why. Then we ask the question, as astronomers, we ask the question, is there life elsewhere? That is the most fundamental question that we want to ask. And we have been searching in our solar system for the last several decades, probably 5 decades, 6 decades, or even earlier. There is absolutely no proof of life yet in our solar system. No proof of life yet. See, I told you everything is work in progress. Yet means still we have not seen. Doesn't mean that it is not there, because it could be there, but we have not been able to detect it. Okay? We haven't seen it. Then we look into our galaxy. Do we see anything? Nope. No signs of life as of today. But we can say, yes, there is life elsewhere. Okay? And that's why it's really puzzling, but we have been at NASA and other space agencies constantly asking this question: how life started here, and can there be life elsewhere? Okay. And for that reason, many missions, many spacecrafts, landers, and all those things were sent to Mars and will be sent to Mars. But Mars is not the only place. We have already have a spacecraft that's going to Jupiter's moon, Europa. Okay, we think that Europa has an ocean where we could probably have conditions conducive for life. But the question of life on Earth seems to have some postulates, working postulates, that we have been looking at. And these are the mainly 3 working postulates. One of them is so-called the Miller-Urey experiment, where they found that lightning in the early atmosphere of Earth could have generated amino acids, which could have started life. The thing that I want to focus on is comets, the impact of comets on Earth. That could have brought not only water, but also the organics onto Earth. And the third one is hydrothermal vents in the sub-ocean surfaces of Earth, where it is known that we have hydrothermal vents, and it is known that there are catalytical reactions happening that could convert carbon dioxide to other molecules. Okay, and this is the Miller-Urey experiment that had been very famous in the early 80s. These are the hydrothermal vents. I have given references. If you want, you can look into it. This is what I'm going to focus. That we think that there were circumstances when comets in the early solar system brought water and the molecules that are required for life to start. Okay? So, before we go to comets, I want to take you back to the origin of our universe, because there are other conditions that are very critical why life has started here. Okay? I'm taking you all the way back to 13.76 billion years into the origin of our universe as we think of now. There was a Big Bang somewhere here about 13.8 billion years ago. And soon after, the first stars were born, galaxies were formed about, a few hundred million years later, okay? The key thing that I want you to keep in mind is that in our galaxy, our sun was born about 4.6 billion years ago. Sorry, because of some, connectivity, it's not coming that strong on the screen there. This is 4.6 billion years, okay? And keep in mind the dimensions of the universe. We have billions of galaxies in our universe, present universe. And each galaxy, like our Milky Way, has a diameter of 100,000 light years. See, I'm talking distance in light years. The distance traveled by light in 1 year is 1 light year. 100,000 light years. This is the enormity of our universe. And there, 4.6 billion years ago, our sun started. Okay? But there are other things. Could life have started immediately after the Big Bang when the first galaxy has formed and first stars were formed? The question is, could it have happened? That's what we call as the population 3 stars, which were the first generation stars. It could not have started because those stars had only hydrogen and helium in the universe. And around the stars, all the matter that was there was hydrogen and helium. Okay? And the second generation stars, we call as population 2 stars, were formed after the first generation stars went through supernovae. That means they burnt all the fuel and then blew off and then put everything into the interstellar medium. Interstellar medium means the medium between the stars in our galaxy. And that material came together to form the second generation stars. Okay? And then when the second generation stars died and exploded, the third generation stars came. That is the population 1 stars. And our sun is one of those population 1 stars. Why is it important? Because if you know life, you know that it is not only water that is needed, organics, that means higher elements, also minerals, even higher elements. So higher elements of the periodic table were required for life to start. And they were synthesized in the stars when the stars were burning hydrogen through nuclear fusion to helium and carbon and oxygen and all those things up to iron, the nuclear fusion was happening. And then when they exploded, all these elements were spewed into the interstellar medium. That would mean that life could not have started in the beginning of the universe. It needed to wait until the heavy elements were synthesized. Nucleosynthesis had happened in the first generation stars and potentially through the second generation stars as well. Okay? And that's why we need to understand what all happened in the beginning, because we needed to wait to get all these elements. These are all essential elements in our life. Okay? That's what is important. Okay? So in our solar system, as you see, we have hydrogen, helium, oxygen, carbon, iron, nitrogen, and also sulfur, magnesium, and all those things. These elements were synthesized in the first and second generation stars. And this is how it would have happened, when we have here the cloud collapse, that means the interstellar medium came together, it started nuclear fusion there, and then you had the first generation stars formed, and they have potentially planet formation, and then mature solar system was formed. In this way, you have the solar system was formed, and then what happens is, sorry for all this, it's not very clear for whatever reason it is. I think that is slightly clear there. So you see that if you have much bigger stars, the lifetime is much shorter. They burn the fuel much faster. And those are the things that actually lead to the second and third generation stars. And our star has a lifetime of 10 to 10 years, and we are halfway through. We are at 5 billion years, or 4.6. So another 5 billion years we have. Imagine if life were to be there, even in a smaller star, it would have 100 billion years of lifetime. That means life can really happen for several, tens of billion years, if not more. Okay? And this is what I showed. On one side, big stars form, and they burn quickly and then emit all the material into the surroundings. The same thing happens to small stars. They also, towards the end, give everything into the surroundings, which we call as a stellar nursery. Okay? That's where all this material will go. Now let me come to what happened to our Earth. Not our Earth, our solar system. Sorry. So, if we see here, this is the biogeologic clock. 4.6 billion years ago is this line. And it is as the time is decreasing towards present day here. Okay, if you see, humans are at the maximum 500, 600,000 years. This is only the humans here. Okay, plants started here. And before that, they were all bacteria and other things. They were found at 3.8 billion years ago on Earth. That was the first time life was detected as per today's dating, 3.8 billion years ago, 3.7, 3.8, okay? But what happened between 3.8 and the formation of our solar system? Several things have happened. This is also important for us to understand why life started on Earth. Can life be elsewhere? Okay? If you want to answer those questions, you need to understand the entirety of it to a first degree approximation. Otherwise, you cannot answer that question. So, as soon as our solar system was formed, there was Earth-Moon formation within 100 million years. Okay? And after that, after a long period of time, between about 4.1 and to 3.8 billion years, there was a lot of change in the positions of planets in our solar system because they were not in stable orbits. Because of that, there was scattering of remaining material in the protoplanetary disk, that is the disk, debris disk we call it as, and they are comet-like materials. They were made of ice, organic matter, and silicate dust, anywhere between 1 kilometer to probably 5, 6, 10, 50 kilometer big chunks of this material. They were not taken to be a part of big planets. And those bodies were scattered everywhere around. And we have evidence for those scattering on our moon. Our moon has craters. If you look through the telescope, I really advise all the students to look, if they have an access to telescope, look at the moon, not on a full moon day, but somewhere in between new moon day and full moon day, you will see craters after craters after craters. Big craters have small craters have little craters. So there is enormous amount of cratering on moon because 4 billion years ago, so many comets and asteroids fell onto this. And still, because moon doesn't have atmosphere, even smaller asteroids falling onto the moon make craters, okay? So that's how we know that it happened, also because of other reasons. And soon after that happened, the first form of life started on Earth. So this much we know. Now, that is what actually made me to go after comets. And I became a part of this Rosetta mission, where we looked at the science of comets. It's called Churyumov-Gerasimenko. It's the two scientists who discovered this comet first, 67P CG. That's why we call it, abbreviating. So that's the comet we went to, okay? So this is what our present understanding is. Something had happened. Now, I want to get you to the uniqueness of Earth. When we want to understand why life is only on Earth, not anywhere else as we see right now in our solar system, we need to still understand better what is unique about Earth. Okay? First thing that is unique about Earth is, as I said, 100 million years after our sun started forming, there was a violent collision between so-called the proto-Earth and another body which was a similar size of Earth. They both collided, making today's Earth and today's moon. Okay? And most recent studies show that approximately until then, it was about half the size of Earth was accreted in the protoplanetary disk, and then you see this jump. This is where another body collided, forming Earth-Moon system here. And today's Earth's mass is that one. Okay? And that collision was important because that collision was so violent that it melted the core and fractionated, leading to molten iron core inside Earth. And that molten iron core gave Earth one of the strongest magnetic field strengths. Okay? Earth has the strongest magnetic field strength in the 4 terrestrial planets. Okay? Without that impact, you would not have had magnetism on Earth. So what are the 4 terrestrial planets? Closest, Mercury. Venus has 93 bar atmosphere, very dense atmosphere here. Earth, and then Mars. We know why Mars doesn't have that much of atmosphere. We think we know conditions when Mars lost its atmosphere and even water on the surface. It is still an active area of research. So Earth, as you see, is the biggest of all 4 terrestrial planets. Mercury has a very small magnetic field strength, magnetism, and it has molten core because of other reasons. Venus doesn't have molten core. Venus doesn't have significant magnetic field. It's only because of the atmosphere, it gains a little bit of magnetism. Earth has magnetic fields, you will see next. Mars doesn't have magnetic fields, doesn't have molten core, doesn't have fractionation. So if Earth were to be as small as the other bodies, you would not have had magnetic field strengths to Earth due to the molten core. And this is where you see that. Earth has about 30 microtesla. The strongest magnetic field is Jupiter, about 400 microtesla. And if you see here, Mercury is small, Venus is small, and Mars is negligible. And other ones are, even Saturn has less than Earth's magnetic field strength. But what does that magnetic field strength do? It forms these magnetic lines which actually enable us to, the Earth to repel the solar wind plasma coming from. When solar wind comes, if there is no magnetic field, atmospheric molecules will be dissociated and you will have runaway chemistry, okay? And that's what actually the magnetic field protects us from losing our atmosphere, okay? The other thing is the impact of bodies. I told you, the comet-like bodies. In order to go to that, I would like to show you how our solar system would have formed. Let's see if it works. We'll see if it works. Okay, let me see. This may work here. So this is how, when there was a disk formed, that is the protoplanetary disk, and when the star forms, and then star has planets forming around it, as the planets are forming, the disk is cleared because all these comet-like materials, small materials, are all taken into the planets. Okay, if it would be like this, nothing would have happened. Okay, moon formation happened, and then nothing would have changed. But it was all different in our solar system. As I told you,
The search for life beyond Earth focuses on three key ingredients. The first one is life's basic chemical building blocks, made from simple elements found in the cloud of gas and dust that gave birth to all of the planets and moons. These chemicals were possibly delivered throughout the solar system billions of years ago by comets and asteroids. But what could cause comets to fly in from the furthest edges of the solar system, slam into Earth, and deliver these organic compounds? The clues to one possible process lie in the Kuiper Belt, the disk of icy objects that orbits the Sun at the edge of our solar system.
We expected when we found the Kuiper Belt that we would just see objects in nice circular orbits about the Sun.
But observations reveal that the Kuiper Belt objects are not orbiting as predicted. Out here,
can you hear in the back?
Levison theorizes that the reason for this mayhem likely is connected with the two largest planets in the solar system. Jupiter is so big it could swallow more than 1,300 Earths. And Saturn, with its vast rings of ice, is 95 times Earth's mass. With their enormous size comes an enormous gravitational pull.
Everything that we see as a result of what Jupiter and Saturn did.
Levison wonders if the chaos of the Kuiper Belt could have resulted from a planet smashing into it. To find out, he runs a number of computer simulations. One model creates the conditions in the Kuiper Belt that we see today. That was 3.9 billion years ago. As Jupiter circled the Sun twice, Saturn made one complete orbit. Each time these orbits coincide, there was a powerful gravitational surge. That pushed Saturn's orbit further from the Sun and destabilized the orbits of the two outermost planets, Uranus and Neptune.
Jupiter and Saturn sort of tugged each other, and that drove Uranus and Neptune absolutely nuts.
Uranus and Neptune are sent careening outwards towards the Kuiper Belt. comets ranging in size from a mile across to objects the size of Pluto are blasted out of their orbits by the planetary invasion.
The disk went, so think of it as sort of a bowling ball hitting bowling pins. These things got scattered all over the place.
The end result is a 100-million-year period when comets, kicked out into the solar system by Uranus and Neptune, smash into anything in their path. It's a period scientists call the Late Heavy Bombardment. This is one theory that might explain how massive amounts of organic molecules, the building blocks of life, made their way to Earth. Possible evidence of the Late Heavy Bombardment can be seen on the surface of other planets and the globes in the solar system. Impact craters.
Literally, the seeds of life, the amino acids, would have been delivered to all the planets and their moons in our solar system.
So if life's building blocks were delivered by comets throughout the solar system, could life also have sprung up on worlds other than Earth?
So, what this one tells us is that when Jupiter, Saturn were not gravitationally in equilibrium, they were pushing everything away in our solar system, early solar system, because of which the comets and asteroids, these are the small bodies that were left over, were sent everywhere. So Moon, Mars, even Mercury and Venus, probably and Earth, all of the bodies got these impacts by these asteroids and comets. And asteroids and comets have minerals, water, organics, all of them what we need for life, okay? And that's what we think was the reason why life could have started on Earth, okay? Can we imagine that before that, if it were to be a solar system where everything was perfect, all the small bodies would have stayed in their position. We would not have had material needed for life to start, most likely, okay? So what are comets, okay? Comets are the most beautiful objects in our sky, present-day comets. When we see them, typically, they're already closer to the sun and their surface gets heated up. And we see this outgassing of volatile molecules and dust. They form millions of kilometers tail. Comets are extremely beautiful in the sky, but their nucleus, that is the real comet, is only a few kilometers in diameter. Whereas we have million kilometers of this beautiful, volatiles going out. So we are going to get one of the rarest comets to our solar system in about 2030, and that would be very big, 200-kilometer diameter almost. It will stay for almost 10 years, but its closest distance to the sun would be somewhere at Saturn, which is 10 astronomical units. Now, let us look into what the comets are made of, okay? These are the comet bodies when they're far away, irregular shape with a lot of, porosity and dents and all those things. They're all made of very small, micron-sized dust and ice grains that actually have been formed in the interstellar molecular clouds between the stars. And these molecular clouds are the nurseries of new stars. Here the new stars are born, and also here are the old stars. When they die, they send all the material into the molecular clouds here. So these are the interstellar ice grains. And these grains become planets when they are, when they have bigger bodies coming together, or comets when there are small bodies. And these comets are everywhere in our Kuiper belt. That is what we talked about in the previous video. And also something called Oort cloud. This is really like a big ball size like thing around our solar system. So our solar system is not only a small disk, but a lot of dots everywhere for several thousands of astronomical units. Okay, that's the thing. And what are those interstellar ice grains made of? If you look into the interstellar space, these are the various material that is there, mostly hydrogen. Hydrogen is the most dominant element in our universe, including in our galaxy. Okay, but when you go to these molecular clouds, you have hydrogen and many more molecules. And if you look here, the density is about 10 to 7 per cubic centimeter. Still, 10 to 7 is still extremely high vacuum in our atmospheric conditions. Okay, in our atmospheric conditions, probably we have 10 to 21, 10 to 22 molecules per cubic centimeter. Okay, and we looked through many telescopes, including the most recent JWST, James Webb Space Telescope. And what you find in this interstellar medium, the molecular clouds, what is their chemical composition, we can confidently tell based on infrared spectroscopy of these clouds. We see a lot of water. This is called amorphous water here because there's no structure. We have carbon dioxide, carbon monoxide, methanol, ammonia, and silicates. All these things are frozen because these grains are at temperature something like minus 260 degrees Celsius, minus 260 Celsius, or about 10 Kelvin, 13 Kelvin, okay? Absolute zero is minus 273, okay? So that cold is this medium. And all these gases are frozen on these small grains. These grains are the beginning of our solar system and comets. Okay, in our solar system, when the sun is formed, all these things are evaporated because it is hotter. But as we go out from the sun, they still remain because the temperature gets cooler as you go out in the solar system. Okay, and what happens when you have these molecules that we have seen in the previous slide? I put it in a different way here. This is the interstellar ice grain composition through the spectroscopy from JWST. This is what we measured from comets when they have this beautiful tail coming out in that. You see how nicely they correlate when we are normalized to water. You have carbon monoxide, carbon dioxide, the most prominent molecules there, and then methane is prominent there, methanol is there, and ammonia is there. So this is the beautiful, correlation showing that interstellar grains, including sulfur-containing molecules, interstellar ice grains are in fact a part of comets. And we see even more chemistry in the comets because the outgassing, we do not see that in the interstellar ice grains because our limitations. Now what we did was, we took these simple molecules and in the laboratory we created the conditions that were there in the interstellar medium, about 10 Kelvin. We froze them. And then we also used the radiation available, mostly high energy photons. And when we use these photons and when we irradiated these simple molecules, water, ammonia, methanol, CO2, and CO, those are very, very primitive small molecules. What happened was, in the lab, when you irradiate and afterwards you warm that up to room temperature and do some analysis, HPLC or whatever it is that you do every day in your chemistry labs, what you find there is that you find molecules that form micelles, you find molecules that are needed for life, like amino acids. Okay, in fact, there was much more work done. See, thousands of molecules were generated from these simple mixture of 4 or 5 molecules. And these thousands of molecules have the properties to form micelles, or amino acids among them, not only amino acids, but amino acids among them. And when you add pyrimidine, you even make nucleobases on that. Okay? And that's what led us to think that interstellar ice grains actually have already the fundamental building blocks of life needed. But you see, all these experiments were done at very low temperature, but the analysis was done at 300 Kelvin. So the question was it required for these comets to come and impact on Earth and warm up to 300 Kelvin to have these life important molecules? Or was it that they're already found in the interstellar medium before even our solar system started? In order to do that, we did some lab work. What we did was we generated that kind of material in this cryogenic system, and we used laser ablation to take the ice into the plume and then analyze the plume through multiphoton ionization process. Spectroscopists here understand what it means. Because of that, we were able to analyze the composition of the ice, and we found that there are several molecules that are required for making amino acids, like methyl isocyanate, acetamide, formamide, and all those things. And interestingly, the molecules that we found in the lab were all found from the comet outgassing in the comet Cherimo-Gerasimenko using mass spectrometry, in situ mass spectrometry, fly through the outgassing of that. And this is another very strong corroboration that these molecules are already there in the interstellar medium, in the ice grains that formed comets. Okay? And our colleagues from there, they have put a lot of names to a lot of things, but they found even oxygen, sulfur, even phosphorus was found. Glycine was found in the outgassing of Cherimo-Gerasimenko. And this is the spacecraft, Rosetta mission spacecraft, and there were several instruments. I'm not sure whether this will come. Maybe this will come. This is a beautiful...
Once upon a time, a spacecraft named Rosetta was launched into the night sky. A long, long journey lay ahead of her to uncover the mysteries of our solar system. Rosetta carried a little passenger, the lander, Chile. Rosetta's exciting mission was to follow the comet as it traveled around the sun. She would learn all about the comet and how it changes as it gets warmer and warmer, while Philae would visit the surface. But as she got closer, Rosetta realized that the comet was much more complex than people had first thought using telescopes from far away. It almost looked like two comets stuck together, and from some angles its shape was really rather strange. It was the beginning of August, and Rosetta had to maneuver several times to get closer and closer to the comet. The nearer Rosetta got to the strange world, the more wonders she discovered on its surface. There were craters, cliffs, and boulders the size of houses. Rosetta spent 3 weeks studying the surface of the comet, sending lots of information back to Earth. On the 12th of November 2014, Rosetta moved into the exact position needed to make sure Philae would reach the landing site. Philae was away. It would take 7 hours to reach the surface, and the moment he had been dreaming of had finally come. As the sun set over Philae's new home, he fell into a deep sleep. One of the most important questions scientists back home wanted to answer was where Earth's water came from. Could it have come from comets and asteroids billions of years ago? Rosetta was surprised to discover that the water vapor flowing away from her comet had a different flavor to Earth's. Comet looked more and more spectacular. Besides water, Rosetta found many other molecules as she studied the atmosphere of the comet, including lots of oxygen. Scientists were very surprised to find so much. They thought that most of the oxygen would have reacted with other atoms, but perhaps it had been locked into the ice when the comet formed 4.6 billion years ago. The scientists were excited by what this discovery could tell them about the history of the solar system. Earth were these important ingredients when our planet was still very young. Finally, after 786 days of the comet, the last day of her extraordinary journey arrived. On the 30th of September, 2016, Rosetta started her descent to the surface of the comet.
So that is the Rosetta mission. I want to tell you something about a mission, okay? This kind of flagship mission, we call it flagship missions, whether it is NASA or ESA. This is a ESA flagship mission where NASA participated. Flagship missions are not one single person's, pride or, what you do or what you get. It is generations, at least 3 generations of several hundred scientists and engineers coming together. So when we want to ask big questions, we need to have not only our ego, but we should put that ego away and work in team to answer those questions. And Rosetta mission was like that. And it took 3 decades to happen. When they started the proposal first, approved in 10 years later, launched another 10 years later, and ended another 10 years later. So 10, 20, 30 years. And 30 years, you have younger generations who came already retired. And those who actually wrote the proposals and got the mission have already died. So you have these generations, and that's why whenever the mission starts, we always recruit younger people, and younger people become the next carriers of this mission, okay? It is generation, it is the humanity that achieves, not an individual.
Whenever I look at a comet in the sky, I always think about this final moment, lifetime of this event.
It was truly a trip to the unknown.
You watch here the diversity of students and people involved in
It's a bittersweet moment, to tell the truth.
I think that it's bittersweet and that it's kind of the death of the spacecraft.
There's great sadness in something that's been a key part of our lives for 25 years.
250 scientists.
That happened in the course of a mission this long. There are people who have passed away. On the other side, there are the babies who've been born.
As time passes, things change, people change.
It's sad, but it has to come to an end at some point.
It's kind of like every mission has to have death because then it leads to birth of other missions. It's kind of like evolution.
When we have acquired a ton of scientific data, there will be analysis for decades.
It's immortality. Data it will be there forever.
I'm not going to say farewell. I'm going to say thank you.
I don't get a sad feeling. I am just excited that we, humankind, know so much more about the universe now, thanks to Rosetta.
But it is leaving us still with a lot of questions.
There are a lot of questions still to be answered. Goodbye, Rosetta.
Goodbye, Rosetta. Thank you so much. Bye, Rosetta.
Au revoir.
Auf Wiedersehen.
Bye, Rosetta.
Goodbye.
Rosetta, great job. You did it. See you around, buddy.
Sleep well. Good night.
Goodbye, and thank you so much.
Bye, Rosetta. Bye, Rosetta.
Thank you, Rosetta, for your dedication to learning the unknown.
Rosetta, thank you.
Rosetta, we are going to be with you all the way in your final journey.
It's been a wonderful, exciting ride.
So as you see, this 3-generational space mission has diversity that you cannot think otherwise. We take pride in our differentness because different minds coming together can make things work, much more complex things work much better because each one has different way of thinking. Imagine that everyone was cloned the same way. Their mind is blocked in the same direction. We need people who think out of the box, and we need them all come together and work together. That's the reason why I really enjoy being a space scientist and exploring, the universe, which is much beyond our normal thinking, and ask questions that are much bigger. Okay. Now, let me conclude here. What we know about the origin of life, or at least the conditions that led to origin of life. For me, there were several accidents, actually. Several accidents that happened to Earth that actually led to conditions that were conducive for origin of life. It was not predestined. Everything was an accident. Violent earth-moon formation gave us magnetism. Other terrestrial planets didn't have it. And Jupiter and Saturn, fighting with each other gravitationally, made water and organics come onto Earth after Earth has cooled down, making perfect conditions for life to start. And, that's how I think we think that these were required. The accidental things that happened on Earth were required in our solar system to have life. Okay? And the another thing that we think is this kind of molecules that are, prebiotic, we call, needed for life, are everywhere. That's what we found from the lab and from the observations. Interstellarized grains are the ones which have already these precursor molecules that are required for life. That would mean that if conditions were to be correct, life may not only happen on Earth, it could happen on many, many other bodies, not only in our solar system, but also perhaps everywhere else in the universe. So it could happen, doesn't mean that it happened or we know that it had happened. Okay? And then we still do not know how these simple or complex organic molecules transformed into macromolecular, biomolecular structures that actually started self-replicating and self-reproducing, which we call it as life. That is still a very big gap in our knowledge. We still do not know how lifeless to life happened 3.8 billion years ago, approximately. And that is what is the job for the younger generation here. Become scientists and engineers and ask that question, how lifeless to life happened. And not only that, accidents brought us the material that is required for life. Another accident happened that actually gave rise to Homo sapiens and us, who actually could speak and communicate and think beyond our normal life. That happened about 60 million years ago. A big asteroid hit the Earth. And imagine that dinosaurs were living on Earth for 200 million years. We are not even there for 0.7 million years. They had been there for 200 million years, and big asteroid came and wiped off 75% of life on Earth. And that actually gave rise to human life. So, heaven gives and heaven takes. Accidents happened. Accidents happened. Accidents happened. And we are here right now. Okay? And that's what is today's, our understanding of how very many accidental things led to life and led to intelligent life, like humans. Now I ask the questions, is there life elsewhere? And for that, we have in the universe has 10 to 21 stars approximately, give and take an order or two magnitude, which would mean that statistically it should be. Professor Husain taught us statistical mechanics and quantum mechanics. He would know that statistically it's not zero. Okay, but only recently we started even detecting other planets around other stars. These we call it as extrasolar planets. And more we detect, more we investigate them in the coming decades, more we understand, could there be potentially life on them? Until then, as I said, statistically, it is S. And there is one very interesting thing called the Drake's equation. This is Frank Drake, who started the SETI search for extraterrestrial intelligence. And he came up with some statistical equation how intelligent life could be there in our galaxy. Unfortunately, many of these probabilities are not well constrained. Because of that, what we know today is probability of finding life elsewhere is anywhere between non-zero and probably 10,000 or probably 100,000. Okay? Yep, that's it. And for now, keep this in mind. There is no planet B. There is no planet like Earth with its biodiversity, its beautifulness, its life. We take it as granted, as I said in my first sentences. There is no planet B. There's no planet like Earth. Okay? It is our responsibility to preserve it and even make it better for living for the next generations. We shall not take life granted. We should not abuse it. We shall not kill it. We should not screw it up. Thank you.
Rather than this writer, you think of what's the right jade bags at this rate, the rabbit that just wanted and why right? That is as like to afford and keep it going. How much life might have actually has there? So slow they just and rather fun to get oxides of hydrogen oxides on the as a very the big about the
the problem is as I said, it is still an active field of research. But the water that came onto Earth was definitely a part of it, at least, is from comets. Okay? But you have to keep in mind that before comets were hitting the Earth went through a violent collision. So we had lost all its volatiles. And there is another school of thought that geologically the water was locked into hydrates and then it fractionated and came out. It is possible. But a part of the water is also from comets. And in fact, most recent studies show that there's D to H ratio of the comets and on Earth are very similar. It is not about exclusiveness. It is about a part of it. And organics were definitely not there before. Organic matter was brought by comets onto Earth. So, and then you also have those other two possibilities for, origin of life through hydrothermal vents and all those. We are not excluding anything. The nice thing is all of them are coming together to one direction, that molecules that were required for life were there, either delivered or made through the lightning or through the hydrothermal vents 3.8 billion years ago. And comets played an important role in that. That's what works.
So I'm just saying that we like after what's combination of just four elements in support body is nice.
Yeah.
But the cycle she is like on the average to like seeing that go on the heads. We get to NHP at TX 4X. All on the main of baby and what was cost atoms to molecules. You were talking about molecules too.
Yeah.
So water was found in the most recent research shows that water could have formed even as early as few hundred million years after the Big Bang. So the thing is, the elements are formed when there is a supernovae. The elements are going through shock wave, and that's when you make silicon oxide. And because this shock wave takes the elements away, and they get cooler and cooler. You make from elements you make molecules during the supernovae. Not only elements, but also molecules. And that molecules, as you go away, they cool down and they form ice. And that's how it happens.
Like a more question. That's smart.
And this, yeah.
We are what are the ingredients that on the get the cycle. So what?
There will plenty of water. Not now. It is every just now that. But I just like to hear from you your comment how that water is okay.
So I just heard recently from a scientist at PRL that actually there was a sudden disappearance of water around 3.7 billion years ago. Okay? Now, this 3.7 billion years, if you look into the biogeologic clock, Earth was hit by another object which became Earth moon 4.5 billion years ago. And then we got all these impacts. And Mars actually got hit by another object 3.7 billion years ago.
Yes.
So after all these water and organics were brought onto Mars, and it had water oceans probably 2 to 3 times atmospheres, one big object came, asteroid or comet, and it evaporated. Yeah, it made everything evaporate. That's how it lost its.
I would like to say that students, especially in school, want to ask anything with regular height. Put them at the carrots. With the school students.
Okay, good.
Hello, sir. My question is, I am very interested in astrophysics. So I wanted to ask what might be any university that I could join for it, or any examinations that are required to join the field.
Very good question. And I keep getting this question. It's a very important question. My answer is, if you want to do astrophysics, okay, you need to build the fundamentals of your education in mathematics, physics, chemistry, and biology, if possible, okay? Have that strong foundations. And then slowly move towards physics. And then you can go to astrophysics.
I can add that point to what Prof Murthy is saying. Our university and a number of other universities and a 4-year undergraduate program in science, focusing on chemistry, physics, biology, and mathematics. So think of that as one possible avenue for going in this direction.
So one important thing is, if you are passionate about something, you don't need to start from LKG towards that. Have the foundations. And then when you go to post-graduation, Ph.D., then you can branch out.
Okay, I'm just yeah. We have
and also here.
After this, one or let me come back.
Dr. Murthy, thank you for an interesting talk. I have a couple of questions. You mainly focused on the comet delivering the organic substances. So do you think the higher percentage of organics that was delivered to prebiotic Earth, was it from the comet delivery, or the prebiotic synthesis processes also, had these basic molecules or maybe amino acids or maybe nucleotides that were synthesized on Earth, on prebiotic Earth? That is the first thing. The second thing is, do we have any evidence of, dipeptides or two-mer RNA or three-mer RNA that is getting synthesized either on comets or the laboratory simulations that are being carried out?
Yeah, both are very good questions. As I told before, for the first question, it could be all and above, because they're not contradictory to each other. It could be all and above. We cannot say which percentage what it is. Okay. Second question is very important. And so far, we have not been able to go to higher molecular polymers and oligomers in the analogs in the lab or from the comets. The next step is to actually find out what are the higher molecules that we can make in the interstellar, material like that ice grains. Most likely, I think the fundamental molecules, simple molecules were made, and when they were delivered, there was this polymerization happened through, dry and wet cycles and all those things. Yeah, that is what we think, but we should never give up. In fact, our lab is going to look for higher molecular weight, chemistry in the interstellar ice grains.
So is there a possibility that people coming to biopics going to the also goes in the science point be like to identify the decision happening on the right?
Yeah, but that's very much possible. In fact, that's what we think right now.
That one's good idea.
Yeah, just thank you, Professor. It was nice.
Just a minute.
Yeah.
Yeah.
Or something, or the what is. So both Earth and Mars like very similar basically. On its water and things necessarily things because they can.
Yeah.
Because so think this event that happened on Mars, but they're asking.
Yes, that's right. 3.7 billion years. And that's the reason why it could have lost. And also Mars doesn't have magnetic field and it's smaller. So it could not have contained the atmosphere. And that's the reason why it lost all its atmosphere. And water was also lost. Okay?
Thank you for delivering such a beautiful and mesmerizing talk. So I was a little bit wondered that you talked that the complex molecule comes from carried out by these comets into the Earth. So my question is how these all the complex molecule distributed throughout this Earth by a homogeneous way. And this is the question. So there is a restrictions and limitations also that whenever comet came to Earth, the time was such that there was temperature was very high.
Yeah.
So in that point, if the complex molecule came to the Earth, then there was a possibility that it may breaks down into its counterparts or a
very good question. And first answer to your first question is that we think that there were millions of comets hit on Earth, not only single comet, millions. They came from every side because we know that moon got it from every side, okay? That's why we had plenty of comets, hitting Earth and gave all this molecule. Second thing is, when the comets or asteroids come through atmosphere, you're correct. Asteroids actually burn and then even explode, okay? What happens is, I said comets are very highly porous bodies. 70% of comet is nothing. Porosity is very high. When porosity is very high, though the surface gets extremely hot, the heat wave will not conduct into the body. We have so-called aerogels. When we have aerogel, which is highly porous, you can heat in the bottom, and then you can put a rose petal on the top, which they did it. Nothing happens to the rose petal. So inside the comet, it was not as hot as outside to kill to destroy all the molecules. That's the reason why, though we lost probably 1 meter of material, majority of kilometer size bodies delivered molecules intact onto Earth.
Okay, one last question. Is
I'm sure about this. It's directly awesome, listen.
Yeah.
When we see atoms, you see that atoms merge together, they form bonds, new organic molecules developed. This bonding happens because they want to be stable. That is, they want to be the lowest potential energy that they can possibly have. Why is it that so? Why do stuff want to stay at a low potential energy?
That you should ask theoretical quantum chemists in this room.
That's me.
So they
will provide an opportunity to visit school.
Yeah. Let me tell you one thing, okay? When you have two or more atoms come together, they have higher energy, right?
Yes.
The higher energy, when you form a bond, that energy is released, okay? And that release in energy makes it to attain lower energy. Okay, so the other reason is if it is high energy system, it can easily dissociate batch. It has to have some binding. Okay, you see, if you are running over a pit,
so it's like a speed pressure. These have less pressure. These have less potential energy. So
exactly. So if you are running over a pit, a big pit, you jump over the pit. You have so much of energy, you jump over the pit back and forth. You never get into the pit. But once you land into the pit, it will not come up. And that's why they are stable.
So, therefore, the lecture is concluded. And I invite Professor Samartha Dean School of Chemistry, to hand over a memento to Professor Murthy. I'm sorry, it's interesting and inspiring lecture. I would like to thank Professor Murthy for taking time out to come here and give this very inspiring and very knowledgeable lecture. And I thank all of you for attending the lecture and participating. I thank Professor Debashish Acharya, head of the Alumni Cell, for his help in arranging this lecture. I thank Dean School of Chemistry and faculty colleagues who all participated. Thank you all. Thank you very much.
So if you want to be in touch with me, you can actually reach me on Facebook. But if you have locked profile, you send me a message and say that I have met you here, I would like to be a friend, and then, or you can send me email. You can find my email on the internet. Okay? But nothing is free. You have to work hard.